Alright, let's talk now about the speed of sound waves. Remember when we talked about waves on a string? The speed of the wave was the tension divided by the linear mass density. Well, the tension was essentially the restoring force, whatever pushed the material back to its original position. And the linear mass density was the inertial quantity, something related to mass that describes how hard the object is to move. In general, this formula works very well for describing the speed of waves. So in general, we will have a restoring property and we will have an inertial property. In the case of sound waves, that restoring property is the bulk modulus. We talked about that back in, I believe it was chapter 14 or 15. It must have been 14. Where it's the change in pressure divided by the change in volume per unit volume. So as we change the volume, we get a certain change in pressure. And that change in pressure causes the system to try and return to its original position. One note, sometimes this is written with a negative sign because a decrease in volume generally results in an increase in pressure. So if that is our restoring property, then the inertial property for a fluid, since it's not just in one dimension but in three dimensions, it's the regular density. Okay. Rho equal to the mass per unit volume. And so the speed of a sound wave is simply the square root of the bulk modulus divided by the density of the fluid or solid or whatever material you're in. I will derive this momentarily, but for now let's focus on the actual result and its implications. So here we look at some densities and bulk moduluses for a variety of materials. So for example, for air at 20 degrees Celsius, the density is about 1.21 kilograms per meter cubed. The bulk modulus is 1.4 times 10 to the fifth newtons per meter squared. If we combine that, take the bulk modulus, divide it by the density, and take the square root, then we find that at room temperature, 20 degrees Celsius, the speed of sound is essentially 343 meters per second. The speed is a little bit less at lower temperature because the gas tends to be a little more dense for a given bulk modulus or a little less springy for a given density. In less dense gases, the speed tends to be somewhat higher. In liquids, even though they have much higher densities, they have much larger bulk moduli. So if you look here, the bulk modulus is 10,000 times larger, which makes the velocity significantly higher in liquids. Notice that in water, it's higher even than in hydrogen. And then in solids, we have an even larger bulk modulus, which results in even larger sound speeds. Now you may ask, how do we measure this speed of sound? Well, there's a variety of methods, but perhaps the most straightforward is the one illustrated here. Suppose we have a very sensitive microphone that picks up pressure variations that go along with sound waves. We're going to see in a moment that sound waves are simply pressure variations. And we place that microphone at one end of a tube, and we snap our fingers near the microphone. Then we get this first peak from the original snap. And this second peak comes from the echo. Now if we can measure the time between the snap and the echo, and we know how far down the tube the sound had to travel, down and back, then we have a distance and a time, and we divide them and get the velocity of the wave. Notice even though the wave travels very quickly, the actual air molecules have not moved that far.